I did. Hopefully this won't be left for 2 weeks like hers has. So that's all I'm really worried about. All right, so we talked about how to do this last time. Just make sure that we remember how to do this.
Determine the conditional distribution.
So what it's not asking you to actually find the PDF. It's just asking you what is the distribution, what kind of distribution is it, and what parameters does it have.
I'm gonna go with normal.
Okay? It's a pretty safe bet. I agree with you. So what do we need to know about the distribution if it's a normal distribution? Mean and variance, good. And we talked last time about how to find the mean and variance. You're welcome. Yeah, we sure did.
That was the expected value.
Yep. What was the formula for the expected value?
Mu of y plus rho times sigma y over sigma x times x minus mu x.
Good. So we just need to plug in those values in this case, right? Mu sub y is 84. Rho is 3 over 5. Sigma y is 8. And sigma x is good. X is, and mu x is good.
I
86.4? So what others got?
probably.
Probably?
Yep. Yes.
Okay, cool. I like verification. All right. So the variance of y, y given x is
Sigma y squared times 1 minus y squared.
okay. And we already said sigma y squared was 64, and the rho is 3/5.
Yeah.
Good. All right. So we also already already established that the y given x is normal. Now we know it has a mean of 86.4 and a variance of 40.96. So that gives us our answer for part A. That makes sense? Yep. How would we attack part B then? Where it asks us to find the probability that 86.4 is less than y is less than 95.36 given x equals 190.
Subtract
Okay?
value and divide by the square root of the variance.
Okay? Which is, in this case, what? Oh, I was actually trying to do the number. That was my problem. I don't know. I was going to write it as square root of 40.96. It comes out even. I just was not having,
That was 6.4.
6 point. Thank you. That's what I was trying to get to. Thank you. I knew it came out even. I was just having a hard time actually getting it to work in my head. And then 95.36 minus the 86.4 over the 6.4. So this is now just like stuff we did for the last test, right? Not much of this is new. Really, the only part that's new is understanding that if you have a bivariate normal distribution to start with, then the individual conditional distributions, either x given a particular value of y or y given a particular value of x, are also normal. And then you can calculate the expected value, the mean and the variance in this fashion.
That's 1.4.
It's 1.4 on the right?
Are we actually find it, or we just don't?
Do you want me to find it, or are you good?
I was just asking. I don't care.
That's the square root of your variance. Right, because it's divided by the standard deviation. I don't care if we find it or not, you tell me.
How do you know that it was the square root of 40.96?
Because I had a 64 out in front, and this is going to be 16/25. That was how I knew. everything was a perfect square.
Yeah.
My brain just wouldn't let me get to 6.4. it literally would not let me get there. I don't know why. I could have told you it was between 6 and 7. I knew it was going to come out even or nice, but I couldn't get to 6.4. Actually, I should have recognized that because 4096 is a power of 2 instead of 64. I know I'm slacking today. I've got a cold. I'm a little off. I mean, I'm a little off anyway, but a little bit more so than usual. What's that?
It's okay, I guess.
Do I need to finish this, or are we good?
We're alright.
We're all right? Okay. Cool. I didn't want to finish it anyway. All right. Let's look at something, well, I'll call it new, but it's not really new. There's only one new little spot that's in section 5.1. And then when we get to 5.2, which probably will not be today, because I'm not doing it today. When we get into section 5.2, it's going to look a lot like what you've done in Calc 3, or have done in the past in Calc 3, when you've changed, say for example, when you change from x, y, z rectangular coordinates to cylindrical coordinates, and you do a triple integral, something has to go in there. Or if you do change from rectangular to spherical coordinates, and you do a triple integral, something has to go in there, right?
The Jacobian.
Yeah, that's what, exactly. So in general, it's called the Jacobian that has to go in there. We're going to have the exact same thing pop up when we do these things in the next section. So you're going to see the Jacobian again. Yeah.
That's fresh in our mind.
Yeah, well, good. All right. This, however, we've already done this stuff. So this is not bad.
Yes.
There's a lot of stuff in... Pardon me.
I'm wrong.
There's a lot of stuff in this section that has theorems in there talking about how to derive these things. In my opinion, there's absolutely no reason to go through the theorems and try to memorize a bunch of theorems to derive these things. We already know how to do it. Why learn new stuff, which is not really anything new? There's just going to be a couple of times where we have to be a little bit careful, but we would have to be careful anyway, even if we were using the theorems. And I'll talk about what I mean when we get there. Let's look at this particular problem. We have a PDF, and we have what we refer to as a transformation of x to give us a new random variable y. Okay? So we have a random variable x. We're transforming x into y, and now we're asked to figure out what the PDF of y is, or more generally, what's the distribution of y. So rather than, like I said, rather than trying to memorize some formula that pops up in the book, let's just do this from first principles ideas. And instead of worrying about finding the PDF first, let's find the CDF, because we can actually do that fairly easily. So if I want to do the definition of the CDF of y, so call it G of y, what is the definition of that? Literally, what's the definition for the cumulative distribution function? Go ahead. It'd be up to a particular value, right?
Yeah.
Of the PDF. But in general, just as a general statement, it's the probability that y is less or equal to little y, right? You were just writing as an integral, but that's the idea, correct? The definition of the CDF is literally calculating the probability that the random variable is less than or equal to whatever the input is. Right? Okay? Well, I don't know anything about y, but I know something about x. Actually, I know quite a bit about x. I know it's PDF. right? So the whole idea here is to convert this into a statement about x rather than a statement about y. What can I plug in for y? X squared. Now I want to try to get x by itself. Yeah, we need to take the square root of both sides, right? For x squared to be less than or equal to y, we would have that x would have to be in between two values. What are they? Negative root y and root y, right? We agree? Okay. Now, in general, this is the kind of thing we'll have to worry about later, but do I really need to worry about this side?
No.
No. Why not?
There's X's.
Yeah, the x is always positive here, correct? So I really don't need to worry about this part. So really, this is the same thing as the probability that x is less than or equal to the square root of y. And again, this is because x is only defined on 0 to infinity, right? No negatives are in there, right? X is guaranteed to be greater than negative root y. We agree? Okay. All right, we said when we started this, we said this was the definition of the CDF of y, correct? What is this a statement about? The CDF of x, right? What number have we plugged into the CDF of x? Root y. Good. So the distribution function, or the CDF of y, is equal to the CDF of x evaluated at root y. Well, how do we get from C? Now, the problem asks us for PDF. How do we get from CDF to PDF? Take a derivative, right? Now, when we differentiate this, what do we have to worry about? What do we have to worry about when we differentiate this? The inside function piece, right? What rule are we going to have to use? Chain rule, right? Chain rule says to do what? Yeah, derivative of the outside. What's that?
Chain rule says to integrate.
It says to integrate? No. We take the derivative of the outside, we leave the inside alone, and then do what? Derivative of the inside, which in this case is 1 over 2 root y. Right? This is Calc 1, correct? And now this piece here, what is f, capital F prime equal to? Yeah, the little f, the PDF, right? We agree? Okay. So going back up here, the PDF was x e to the minus x squared. Yeah. So here we'll have, instead of x, we'll have square root of y, e to the minus square root of x squared. Oops, sorry, square root of y squared. Because it was x e to the minus x squared, right, for the PDF? Okay. And then we'll have times the 1 over 2 root y. So we just end up with 1/2 e to the minus y. We're done.
You forgot the over 2, Dr. Joe.
I forgot the what?
Over 2 in the exponent.
Oh, was there an over 2?
Yeah.
Oh, my bad. Okay.
So you're just plugging the square root of y.
In for x.
If I ask why, would you get mad?
Why would I get mad if you're asking a question?
Why?
Why would I get mad for you asking a question?
Because sometimes I ask stupid questions.
No.
There are no dumb questions, Grace.
All right, so
Pertain to class.
it's true. She's right.
That's a direct quote from Dr. Joe.
That's right. So here, this is a, what does this say to do?
How do we know the noun pertains to y? Like the little f?
The little f doesn't pertain to y, it pertains to x. We're putting in the square root of y for x.
I'm saying the function of x equals square root of y.
You're okay with this step here?
Yeah.
Okay. So this is a statement about the CDF of y. We're relating it to the CDF of x. Yeah? Okay. So this says that we're going to take our PDF, and wherever we see the x, we're going to put the root y in.
The PDF of what?
The PDF of x, to get the PDF of y.
Oh, we have the PDF.
Yeah, we have the
See,
PDF of
that's
x.
where I was.
Ah, there you go. Yeah, Megan.
Where does the 1/2
Where does it come from?
Yeah.
Yeah, we're taking the derivative of the square root of y. So you get y to 1/2, so it's 1/2 y to the negative 1/2. So I just rewrote it that way. That's where that comes from.
So this, what we said this is equal to?
Well, the problem just asked us for the PDF. So this is the PDF of y. Yep. What kind of PDF is that, by the way? You should be able to recognize it.
That's an exponential.
That is an exponential. What's theta?
1/2. No, 2.
2, yeah.
Damn it.
No one okay?
Also be a chi-squared.
It could also be a chi-squared. What would r be in that case?
1.
I don't think so. I think r is 2 in that case.
Oh yeah, yeah.
Okay. Yeah, it's gamma of alpha. If gamma of alpha is 1.
Yeah.
Yeah, so we can think of it as 3 different ways.
Is gamma of 2 also?
Say it again. Is gamma? Yes, because gamma of 2 would be 1 factorial.
Yeah.
That one okay?
Yeah, it should.
Was this anything new?
No.
No. Good.
I would not be able to do that on myself though.
Good. I'm glad you recognize this as a no. All right. Try this one. I think I actually have handout for this.
We dropped one.
I did. You're welcome. You're welcome. You're welcome. Yep. You're welcome. Yeah.
Inverse.
You're welcome. Sorry. Little pieces of chalk drive me nuts. Not the only thing that drives me nuts.
To the cleaning staff, right?
Or I could just be nuts. It's fine. The cleaning staff not putting the chalk back on the chalkboard tray when they're done at night? Yeah, that one's driving me nuts right now.
You never leave it.
I have, not this year, but I have been in classes where they've completely had the eraser soaked the next morning.
That happened to Dr. Olson.
Yeah. That's
Was
just annoying.
You switch this with your eraser.
Oh, yeah. I was surprised he's hiding the chocolate on that list.
No, that's actually funny. That amuses me.
That was fun.
Now, Ryan and Nothing Water on the eraser, not fun. That was too far.
I don't remember that one.
That
That was
was
it.
too far.
That was too far. That was abstract.
Oh, that's what
That's right, that's.
That was the daily thing. That was a daily. Yeah, that was a daily thing.
That's awful.
It was fine.
We play by the chalk. Class starter.
Mm-hmm. It was. Yep. Find the chalk.
All right.
Oh,
Dr. Joe, do you know what the answer is?
no. I didn't do the problem.
Dr. Joe, you still said the answer.
I can do the problem. We'll figure out the answer in a minute. You gonna come write it up here again?
Dr. Joe, I got an answer.
Oh, good. You wanna write it?
Yeah, sure.
Okay.
Wait, you gotta check it first.
I have to check it first.
If I'm wrong.
If you're wrong, Grace, take on the team.
It looks good.
Big bet.
Do I have to write down all my work?
You should probably write down some work.
How do I move the screen without writing on it?
Just scroll with your finger.
Oh, okay. This is nerve-wracking.
It's nerve-wracking?
Yep.
Kind of in theory.
Yeah, but now Michael's here to make fun of me. Like,
You know, Michael's always around to make fun of people, though.
Dr. Joe, am I not allowed to put my wrist on this?
I do.
Oh, you do? This is supposed to be an uppercase Y, so just so you guys know.
So you underlined it 3 times to get uppercase?
Yep, grammar.
Bless you. Or learn how to sneeze like Dr. Raw. Hot chewy! Every time. Yay! Know what others got?
Yes.
Oh, cool. Good. I didn't have to say anything. That was fantastic.
Dr. Joe, do the bounds matter? Because in my problem, I didn't use the bounds for what Y is supposed to be. They were like,
They just told you for certain what the bounds had to be, so we can notice that by the fact that the square root function is increasing. We can just plug in the endpoints. So when x is 1, y is 1, and when x is 2, y is root 2. So
if it said like 4 and square root 8, can we not do that?
it wouldn't have been, yeah, that wouldn't make any sense for this problem the way they define the PDF for x. Because the y values depend on what the x values are. All right? Yeah, okay, well, if you understand that one, I'm not going to bother with that one. Let's see if we can do this one. Mainly to see if you can identify what the distribution of y is. Sorry. At least only one of you has to listen to me do it for the next 4 hours in the car.
You drive 4 hours to work.
No. Yes. You caught us. Great job. Actually, wasn't a walk.
I did this. That commute's brutal, let me tell you.
Are we going part of the way?
We're going to Atumwa, which is about 45 minutes short. Because the breakfast options were better at Atumwa than they were in Pella. That was exactly how I chose it. I cleared it with Sid first, so.
All right.
Yeah.
Sounds great.
I wonder where Marshall was today.
Yes, if popular physics was, I'm sure they just didn't show up to these classes because he would forget to come to a physics class to proctor the test.
Man. Okay.
Got told.
Your face would have reminded me, hopefully. If not, your mouth would have.
I wouldn't have reminded him. I wouldn't have said anything. Wouldn't have talked about physics at all. I would have made sure that he would have forgotten. So I could just leave it. No, because there would be nobody to give me a test in the first place.
Ashley's drawing pictures now. Are we done with this one?
No.
Okay.
Gosh.
I don't understand.
No, she was drawing circles. It was like doing the compulsories for figure skating competition. Figure eight, figure eight, figure eight.
Dr. Joe, when I take the derivative, what variable do I take it with respect to?
The y.
But there's two variables in y. There's x and theta.
No, there's only a y. We have to solve. The first thing you want to do is solve for the x so that you can write your cumulative distribution functions in terms of y. The theta is a constant here. Have you gotten to do at least this point?
Yes.
Okay, did you remember to flip your inequality?
No. Yes.
No.
I did.
Nailed it.
Ah! Negative 2 theta, so when you divide that over, it flips the inequality, right? Yeah. Gotta remember to do that.
1 minus now?
Yeah, you do a 1 minus. Yep.
So how does that affect the rest of it? It's-
Honestly, the only thing it does is make sure that you don't have a negative PDF.
But if I just go all the way through, if I multiply by -1, would that be?
It would be in this case, yes. Well, in all the cases it should be. The reason why is when you take this derivative with respect to y, you're going to get a negative that pops out. It means it cancels with something. Right? When I take this derivative, eventually, a negative is going to come out. I can't have a negative PDF. So that's why it's important in this case. It is something to be careful of. What they do in the book, when they have you memorize a theorem, essentially, is they take care of it by working with the absolute value.
So I got this really ugly. So if I just get rid of that negative, is it the same thing?
So what is this, after the minus sign, what is this equal to now? Oops. F of what? Good. We all agree with that?
Yeah.
Okay. So notice that our first step here in these problems is to be able to solve for the x, right? And essentially, if you read through the book, what we're doing here, when we're taking, we've got y as a function of x, and instead of solving for x, we're finding the inverse function. Right? We're undoing what has been done to the x. Okay? So now we want to take the derivative. Oops, not a little g though. Oops. Try it. Keep forgetting my minus sign. Whoa, that was really weird. So when we take the derivative of the 1 is 0, right? So the minus stays there. We get capital F prime of the inside times the derivative of the inside with respect to y, which is why that's negative 1 over 2 theta.
Why is the
Say it again?
why is the
Oh, because I forgot to take the derivative of it. Sorry. Oop. It didn't disappear. It's there. I just forgot it. Try that again. I got to do derivative of e to a power. Thank you. Derivative of e to the power is e to the power times the derivative of the power. This now goes in where? In the PDF, right? So we get negative theta times e to the minus y over 2 theta to the theta minus 1.
yes?
And then times e to the minus y over 2 theta times negative 1 over 2 theta.
Oh, wait, we don't distribute to the 1?
Is it okay to just get rid of the two numbers?
Yep.
Make it positive?
Okay, I'm going to simplify this a lot here in a second. Because this is going to simplify actually quite nicely. Ouch, that really hurt. It asks how y is distributed. Do I recognize that distribution the way I've got it written right now? No. So it better be a little bit nicer somehow. So yes, like Ashlyn said, we can get rid of the negatives, right? We can cancel the thetas. What do we do with the exponents here?
Add 1 to the theta minus 1.
We multiply those together, right? And then add this one on. Okay. Well, notice when we multiply the theta through, you're going to get e to the negative y over 2. Right?
Yeah.
And you'll get a plus e to the y over 2 theta. Then I've got an e to the minus y over 2 theta. So this whole thing is going to simplify to, I've got the 1/2 on the end e to the minus y over 2.
How do you do
I just do that in magic. I'm a mathematician. Oh, seriously? Come on, that's not bad. That's not even mine. That was one of my students from several years ago. Talking about Fubini's theorem in Calc 3. About how you can replace the double integral with a double iterated integral. It's called Fubini's theorem. He said Fubini was a mathematician, but it's not like Fubini. So, can't even take credit for that one, but I liked it a lot. So that's why I stole it. I don't think it was intellectual property. I don't think he had it filed. It's fine.
I use that one too. Is that-
Okay. All right. This okay?
No.
What's wrong with it?
Can you do the algebra?
Take this theta and multiply it over. What do you get?
Negative y over 2.
Okay, so that's where that's coming from. When I take this -1 and distribute it, what do you get?
You get 1 over that.
No, I'm taking -1 times it.
Oh, you get y over 2.
I get y over 2 theta, and then I've got a minus y over 2 theta. Those cancel each other out when you add them.
You can also just add, so that the e to the negative y over 2 theta.
I could have just added up. I could think of this as, if I do it that way, I can think of this as to the first power, and then just add the two together, and get a theta, and like you said, and then just distribute it that way. And then you just have a theta and an over theta. So anyway, what kind of distribution is this?
Exponential.
It's exponential again. It's the same one we got before. Hey, look at that! All right. Let's see what we got. Oh yeah, let's look at this one. So this looks a lot like the first one that we did, but we have to be a little bit careful. So let's go through this one together. It asks for the density function, so PDF, of y equals x squared if our PDF for x is 1 minus absolute value of x. All right, so same principles that we've been doing. Set up our CDF definition and replace the y with x squared. Now this looks a lot like the first problem we did, and you told me correctly how to rewrite this. How did we rewrite this when we took the square root? Yeah, negative root y to root y, right? Now does it matter in this? Does this negative root y matter in this case? Yeah, it sure does, right? It matters because our x's can go all the way down to -1. So I don't want to get rid of it this time like we did in the last one. In fact, this illustrates one of the problems that pops up when you work with these, is that y equals x squared doesn't have an inverse on this interval. Right? It's not 1 to 1. It's 2 to 1 on that interval, right? It's a piece of the parabola. Okay? So we have to be a little bit careful, but if we apply the same principles, we can get the correct answer without any issues rather than having to go through memorizing a formula that they talk about in the book and worrying about is it 2 to 1, is it 1 to 1, what is going on. So in this case, I can still rewrite this as a statement involving the CDF of x. I just need to use it twice. I can rewrite this as capital F of root y minus capital F of negative root y. Right? Because all we're doing is subtracting off the piece that we don't need at the end. So we've done the exact same thing that we did in the previous examples. We've rewritten the distribution function of y in terms of the distribution function of x. So what's the next step? Take the derivative, right? So little g of y will be the derivative of capital G of y. And then we need to take the derivative of both of these pieces. The first one will be capital F prime of root y times 1 over 2 root y. And then we get minus capital F prime of negative root y. And this will be times negative 1 over 2 root y. Everybody see that? Anybody else sick of my coughing? Sorry. Okay, so this says to put square root of y in the PDF. The PDF was what? 1 minus absolute value of x? Okay, so this is going to be 1 minus absolute value of root y times 1 over 2 root y. And we get the same thing here, but this will be a plus. We'll have 1 minus absolute value of root y times 1 over 2 root y. Oops, got a negative in there. But at this point, I'm just literally taking the inputs and plugging it into the PDF. What does the absolute value here do to the root y? Nothing, right? Because root y is positive. What does the absolute value do to the negative root y? It just changes it to positive root y, right? So we've got the exact same term in both spots added together, so we can put this all together to give us, we can write this as 1 minus root y all over root y. Because it's a 1/2 of each of them, right?
When we got to the step with when we have that root y minus that negative root y, can you rewrite that, bring the negative out front in the second one? And have it be 2 f root y minus 1.
Say where? Here?
No, up on line.
Oh, this one?
Yeah.
You could, in this case, because it's symmetric. Your PDF, right? Your PDF had to be symmetric to start with. That's why I just left it.
Okay.
Yeah. In most cases, it will be symmetric, and you'll be able to do that. But in this case, the reason why you could do what you just said you could do is because of the symmetry here. So that's why you can do it that way. Yes. I'm adding them together. It's basically taking a half plus a half. Yep. Because if I think of the 1 minus root y over y as x, I've just got a half x plus a half x. So the 2 just goes away. That one okay? All right. Let's see how this differs a little bit from this problem. Maybe. All right. So this looks similar to the previous problem, except the PDF's different, but it looks similar, right? This is the 3rd time now that we're doing the PDF of x squared. Now, remember the previous problem, however, I know it was a different PDF, but also the interval is different. The interval went from -1 to 1, which when you square it, folds exactly on top of itself, right? Right? When I square it, does this one fold exactly on top of itself? No, okay? So we're going to have to do this in cases. We'll have a case where it actually does fold over the top of itself, and then have the case where it doesn't, okay? Pardon me. So what part of this will fold over the top of itself? The -1 to 1, right? When we square it, right? So from -1 to 1, that becomes just 0 to 1, right? Technically, I'd have a bracket, but the point itself doesn't matter. Then the 1 to 3 becomes what? What happens when you square it? You get 1 to 9, right? So these are your x values, correct? And what's the transformation? They're squaring, correct? So these are my x's, these are my y's after I square. So what we're saying, basically what I'm saying here, I draw the picture over here. You've got a number line, you've got -1 to 1 and a 3 here, right? When we do the squaring, this interval is going to get flattened over the top of itself, right? That interval is going to become this. Right? This is a 2-to-1 mapping. It gets smashed on top of itself. Right? But from here to here, it's just a 1-to-1 mapping. Right? When I square a number between 1 and 3, I know it has to be between 1 and 9. And if I go the other way, I know it had to start between 1 and 3. Right? If I start between 0 and 1, I don't know if I was between 0 and 1 to start with or between -1 and 0. That's why I have to handle them separately. Okay? So this is going to be ended up being a piecewise defined function that we'll have at the end for our PDF. Let's see why. And I'll hurry. This part we've written a few times, right? Oops. And negative root y is less than x is less than root y. Now, when's the only time we have to worry about the negative root y part? What does y have to be in order to be able to worry about that? So if y has to be between 0 and 1 to even worry about this part, right? Because if y is bigger than 1, x is guaranteed to be bigger than that. X can't get less than -1, right? So for example, if y is 4, that would say that x is greater than -2, which has to happen, right? X can only be between -1 and 1, right? So this is equal to a piecewise defined idea. This is equal to capital F of root y minus capital F of negative root y if y is between 0 and 1. The part where we have to worry about folding over the top of itself, and it's just capital F of root y, I'll leave it now, if the y is between 1 and 9. Because again, the other part's guaranteed, right? Or think of it this way. That second piece of the difference is saying it's the probability that that x is less than negative root y. If y is bigger than 1, the probability that x is less than negative root y is 0. So there isn't a minus part there. And then to finish this off now, you'll still differentiate, you'll just have to do both pieces. You'll finish this just like we did. The only thing I'm saying here is we have to be a little bit careful when you've got pieces that fold over the top of themselves, when you don't have a 1-to-1 mapping. Okay. So they require a little bit more thought, but the process is the same once you figure out what the thoughts are. Okay, Megan?
Why isn't the range to the top one?
Because the range is in terms of the y in this case, because we're trying to find the CDF of the y. Since y is x squared, y can't be, y is 0 to 1. In that case. That makes sense? Okay. All right. Have a good one. And we'll see you Monday.